Hey guys, so my name is Tyler, and I'm going to be talking about the power and absorption of electromagnetic waves. And we're going to start with talking about the power. So the power can be defined by the Poynting theorem, which describes the power flow of an electromagnetic wave. I'm just going to start by drawing a diagram of the electric and magnetic fields of a simple plane wave. So the red illustrates the electric field, and as you can see, it is polarized in the x direction and it is propagating in the z direction. And now this blue wave is our magnetic field. It is always going to be perpendicular or orthogonal to the E field and is polarized in the y direction and propagating in the z direction. So power and the Poynting theorem is defined by S, which is equal to the cross product of the electric field and the magnetic field. So from our diagram you can see that our S vector is always pointing in the positive z direction. So we're just going to write down a couple of Maxwell's equations so we can derive where the Poynting theorem comes from. And so our first equation is the curl of the electric field equals the negative time derivative of the magnetic flux density. And then our second equation is the curl of the magnetic field equals the time derivative of the electric flux density plus our electric current density. Our equation on the left hand side is Faraday's Maxwell's law, and our equation on the right side is the generalized Amperes law. And so in order to derive this, we're going to have to kind of mess with the equations a little bit. So Faraday-Maxwell's law, we're going to dot with an H field, and the generalized Amperes law, we're going to dot with an electric field. So we can rewrite this out as the curl of the electric field dotted with the H field equals the negative time derivative of the magnetic flux dotted with the magnetic field. And then on our right hand side, we have the curl of the magnetic field dotted with the E field equals the time derivative of the electric flux dotted with the electric field plus the dielectric current density dotted with the E field. So now we're going to subtract the two equations. So have Faraday-Maxwell's new equation subtracted by the generalized Amperes law. And we're going to get this. And so as you can see, it is getting a little messy now. And so we are going to look for a way to simplify our equation. So there's a vector cross product identity, which is the divergence of A cross the vector B equals the curl of vector A dotted with vector B minus the curl of the vector B dotted with the vector A. And so if we look above in our equation, we can see we have the right hand side of that, and so we can substitute the left hand side into our equation. So now for our left hand side, we have the divergence of the electric field crossed with the magnetic field. So now we're going to take the integral of both sides with respect to the volume, and we'll have on the right side the integral of all of this. So we are going to be using our divergence theorem in order to simplify down our left-hand side. So that will give us now the integral of the electric field crossed with the magnetic field times ds, and that equals our right-hand side. But for our right-hand side, we're going to currently assume a simple media approximation, which makes our J equal to the conductivity times the electric field, and our magnetic flux to equal mu times our H, and our electric field equal our magnetic flux density divided by epsilon. So in this case, our mu is our permeability, and our epsilon is our permeability. So now we can rewrite our right-hand side as the negative integral of mu times the magnetic field dotted with the time derivative of the magnetic field, plus epsilon times the electric field times the time derivative of the electric field, plus the conductivity times the magnitude of our electric field squared. And this is all in respect to dV. And so we can sub in our Poynting vector into the left-hand side, which shows that E cross H equals S. So now we have on the left side the integral of S times dV. This equals our right side. If we pull out the time derivative, we get the negative integral of the time derivative of mu times h squared over 2 plus epsilon E squared over 2, all plus sigma times the magnitude of the electric field squared in respect to dV. And for this, we can see on the right-hand side that there are two different things. So the first function is the energy density of field, which is the rate of loss of the electromagnetic energy stored in the field. And the second part is ohmic loss, which is the rate of energy gain in the particles. And this all equals the left-hand side, which is the rate of energy transfer out of the volume. So in almost all circumstances, it's more useful to determine the time average power instead of the instantaneous power. So here I'm going to describe how to find the average power. So our electric field is E naught times e to the power of j omega t in the x-hat direction, and our magnetic field is equal to h naught times e to the power of j omega t in the y-hat direction. Again, this is because they are perpendicular. Now we are going to want our electric field and magnetic field to both be the real parts of these functions. So we're going to rewrite this out as real and assume h is the same. And then we are going to rewrite out our whole function in terms of a real and a complex part. So we can separate out our E into an ER for electric field real and EI, which is electric field imaginary. And then using our Euler identities, we can then rewrite our electric field in terms of its real components, which is E equals ER times cosine omega t minus EI times sine omega t. This is all still in the x-hat direction. And similarly, we can write our magnetic field as HR times cosine omega t minus HI times sine omega t, all in the y-hat direction. So we can now describe our Poynting vector as S equals E cross H. Let's get ER times HR cosine omega t squared plus EI times HI sine squared omega t, and then minus ER times HI cosine omega t sine omega t, and then minus EI times HR cosine omega t sine omega t. And then we are going to calculate the average power from this using the formula 1 over the period times the integral from 0 to the period of the Poynting vector dt. So we can tell that in this equation, once we plug it into the integral, that our right two-hand terms will go to 0, and that is because of these integral identities we know. So the integral over a period of 8 sine omega t times cosine omega t equals 0. And then for the other two, we know that the integral over a function of a times cosine squared omega t equals a over 2 times the period, and the integral over the period of a times sine squared omega t equals a over 2 times the period. So this gives our average power to be 1 over the period of the ER times HR over 2 times t plus HI times EI over 2 times t. So simplifying this down again, we can cancel out the t's, and we get our average power equaling to 1/2 times ER HR plus EI HI. And we can prove this equals 1/2 times the real part of the electric field crossed with the complex conjugate of the magnetic field. This can just be easily shown by rewriting exactly what that means. And that is the 1/2 times the real part of ER plus J times EI x hat crossed with HR plus JHI y hat. And if you do the math, you will get the same solution we had above. And so that is it for our power. And so now we are going to move on to our second part, and that is talking about the absorption of an electromagnetic wave in a conducting media. So for this, we're going to start with the same two Maxwell's equations that we started with before. So the curl of the electric field equals the negative time derivative of the magnetic flux density, and then the curl of the magnetic field equals the time derivative of the electric flux density plus J. So this is again Faraday's Maxwell's law and the generalized Amperes law. So we're going to assume simple conducting medium, and also we're going to use phasor notation, which turns all of our derivatives into J omegas. So as you can see, we've substituted mu h's for b's and epsilon e for our d. So we're going to again manipulate these equations, but we're only going to manipulate our Faraday-Maxwell law by taking the curl of it. And when we take the curl of it, we get the curl of the negative curl of the electric field equaling to J omega mu times the curl of our magnetic field. And then we're going to sub in our generalized Amperes law into that cross product of the H field. So we get our right hand side now equals J omega mu times J omega epsilon times the electric field plus sigma times the electric field. And now for our left hand side, we can use a vector identity to show that this equals del squared of the electric field. And for our right hand side, this still equals J omega mu times J omega epsilon E plus sigma E. So we can move our right hand side over to the left hand side. Then we get del squared of the electric field minus J omega mu times J omega epsilon E plus sigma E equals 0. And this looks awfully familiar to our old wave equation. With our wave number being in that negative portion right there. So our new wave number is this gamma squared, which equals J omega mu times sigma plus J omega epsilon. And this wave number can be broken up into two parts. Our alpha plus the imaginary part is a beta. And our alpha and beta are very similar. If you solve the equations, you can get these two equations for our alpha and beta. So there's just one difference. The alpha is omega times the square root of epsilon times mu over 2 times the square root of 1 plus all in brackets sigma over omega epsilon squared minus 1. And the only difference is the beta is plus 1. So what we can notice is our wave number is now complex. It used to be just our beta, but now we have a gamma. So now we are going to solve the wave equation. And this is just going to be for one directional travel or propagation in the z direction. So we can change our del squared to the second derivative of the electric field minus our wave number times the electric field. And this all equals 0. So solving this out, we get our electric field in the z direction to equal E naught times e to the power of negative wave number times z. And this is in the x-hat direction. And then again, we are going to take the real part of it because it is time harmonic. And we get the real of E naught times e to the power of negative alpha times z times e to the negative j beta times z times e to the power of jwt, which accounts for, again, the sinusoid. And writing this out with our real part, we get E naught times e to the power of negative alpha z times cosine omega t minus beta z, all in the x-hat direction. This is our electric field. So as you can see, that term, the e to the power of negative alpha z, is our absorption. So what that does is it reduces the electric field in the media. Our H field, or our magnetic field, can be found similar, and that equals the electric field over our impedance, which is now complex, times e to the power of negative alpha z times cosine omega t minus beta z in the y-hat direction. So now our impedance, as we said, is complex, and this equals the magnitude, and then also a phase shift, which is denoted as e to the power of j sigma n. So if we rewrite all of that back into it, we could get our magnetic field as equaling E naught over the magnitude of the complex impedance times e to the power of negative alpha z times cosine omega t minus beta z minus sigma n. And this is all in the y-hat direction. So yeah, I'm just going to draw out how the media affects, how the conducting media especially affects the electric and magnetic waves. So again, with red, we are going to draw the electric wave. As you can see, it's still polarized in the x direction and propagating in the z direction. And then with our blue, we are going to draw our magnetic wave, which is still polarized in the y direction. So as you can see, they are no longer perfectly in phase together. They are out of phase by a certain margin. And also, if we're just looking at the electric field, there is an exponential decay of the wave in the conducting media. So we're just going to write that out. And yeah, that's the effect for what happens in a conducting media with absorption. So thank you for listening, and I hope you guys learned something. Yeah, take care.